There we go.
There we go. Okay.
Right, we're all set.
All dicks, everybody.
Easy people. All right. So I'm the co-founder and CEO of InfluxDB, which is an open source time series database that we've written in Go. So this talk is Go snippets from the InfluxDB storage engine that we're creating right now. Actually, I should probably call this talk the InfluxDB storage engine and a sprinkling of Go, because when I was thinking about what to do, like what to talk about and what would be interesting, I thought, okay, given the other people I'm on stage with over the course of this day, I can't really tell you anything about Go that they can't tell you. They know a hell of a lot more about the language than I do. So I was thinking, what can I pull from my recent experience that might be interesting? So I have a couple of Go things, but it's also a talk about our storage engine, which we're building right now. So a little bit of preliminary info so you can get the context for the problem and kind of frame things. So this is what data looks like in InfluxDB, right? We have a measurement, which is just a name. We have a set of tags, which are key value pairs that are strings. We have a set of fields where we have a field name and then a value, and the value can be a float 64, an int 64, a boolean, or a string. And then finally we have a timestamp, right? That's just an epoch. Now the truth is, in InfluxDB we can represent timestamps at the nanosecond scale. I just didn't put that in here because it wouldn't fit on the slide. So, digging a little bit deeper into that, we have the measurement, the tag set, and then the field name, and this gets converted into a unique ID. So basically, if you look at that, with us like splitting them out, splitting the different fields into separate IDs, we're going to push the data onto the disk and arrange it kind of like a columnar store, instead of a row-based storage engine like you see in Postgres or MySQL or most SQL databases. So the data per ID is then ordered by time, and the tuples are just the timestamp and then the value, right? So looking at this, arranging it in a KeyValue Store, which is what many storage engines are, they're really just KeyValue stores. Here we have the key. It's a composite key where the first part of the key is the ID of the series, and the second part is the timestamp, and then we have the value itself, right? So here we see two keys, the two different IDs, the two different values that we had before. And here if we insert a new value, we see that it goes in the middle there, and the timestamp is just 1 second greater than the previous one for one. So that's an important distinction when we're looking at these storage engines, is the key space is ordered. And for the time series use case, we use that because we scan over this data to compute aggregates and do downsampling and that kind of stuff. So here, looking at the key space with more, a new ID in there and other values, we can see this is what the data would look like arranged in the key space if we were going to visualize it. So there are a lot of existing storage engines, open source, that have this model, right? There are key value stores where you can do a put, a get, a delete, and the key space is ordered. And you can range through the key space, right? So if you seek to a certain point, you can just iterate over it, right? Now, since there are so many open source storage engines out there, why in the hell would we write a new one? I heard a stat the other day. Somebody said it takes 10 years for a new storage engine to get to maturity. So why would we embark on this 10-year journey if other people have already done it, right? We could just use MySQL's engine or Postgres or whatever. So this was kind of the journey that we've taken over the past couple of years. So first we used log structured merge trees. The most popular use of this is probably in Cassandra. So this is what Cassandra uses to store the data under the hood. It's something called the log structured merge tree. There's an open source library at Google called LevelDB, which allows you to just embed a log structured merge tree in any program that you write. Now the problem we had with that is that deletes in log structured merge trees are expensive. And in the time series use case, it's very common to delete large ranges of data after you've downsampled it and you don't care about it anymore. And the other problem we ran into is that it resulted in too many file handles, right? So we had tons of files open. We would actually hit the limits of the operating system when we were using log structure merge trees under the hood. So then the next iteration, we said, okay, LSM trees aren't going to work. LevelDB is not going to work for us. So let's try a memory map copy on write B plus tree. One popular implementation of this is called LMDB. We used one that's a pure Go implementation called BoltDB that was written by Ben Johnson. It's an excellent library and it works really well and it's very mature. But we had a couple of problems with it that were kind of insurmountable for our use case. The first, write throughput. So copy on write B plus trees people know them as being optimized for reads. And we found that the write throughput wasn't good enough for our use case. And particularly, the write throughput got really bad as the database grew in size. And again, for time series data, we're really talking about scale, so size is the thing that actually matters. We need it to perform well when the database is very large. And the other big problem we had was compression. There was no compression, right? LSM trees, LevelDB specifically, has compression built into the library. Copy on write B plus trees generally don't have it built in. Bolt certainly doesn't. So basically what we found is that for these two storage engines, they didn't meet our requirements. So just to review really quick, here's what those requirements are, right? We have high write throughput. We want to be able to sustain 100,000 writes per second, more if possible. We want to get awesome read performance. Every query that we do against the database isn't hitting a single key value pair. It's hitting a whole range of key values, right? Because you're computing like percentiles or counts or whatever. You're computing some aggregate over time. So we need to be able to scan through those very, very quickly. We want to achieve very good compression because if people are collecting billions of data points a day, a few bytes with every single data point actually makes a difference. Normally you don't care about a few bytes, but if you have a billion points coming in, a few bytes means the difference between keeping your data for an extra 7 days versus throwing it away in an hour. So some of the other weird things that we have is we have a requirement where we don't want writes to block reads. We always want to be able to write to the database. But at the same time, reads can't block writes to the database. And more importantly, we want to be able to write multiple ranges of time simultaneously. So again, like all of our data is arranged by time. Most of the time we're appending new data, but if we append data in the past, we want to be able to do that without affecting the performance of appending the new data that's coming in that's really hot. We also need hot backups. And this was the thing that actually killed us with LSM trees and LevelDB, is we need to be able to open many databases in a single process. So basically, we arrange the data in multiple databases in blocks of time, and we need to be able to have many of them open so that we can drop them quickly if we need to evict old data, and also move them around. And if we have a cluster of machines, we want to be able to say, this machine needs to move this data over here, and we can just move a block of the key space very efficiently by moving files around, as opposed to copying raw values. So this is what we're actually working on right now. This is for our next release. We're tentatively calling it the time structured merge tree. It's kind of like an LSM tree, but it's a little bit different. I promise there's Go code coming, by the way. It will happen. I wasn't lying. So the components of this thing are, you have a write-ahead log, you have an in-memory cache that keeps the data from the write-ahead log, and you have a bunch of index files. This is very similar to how LSM trees look, right? LSM trees have a write-ahead log. They have an in-memory cache, which are called mem tables. And they have index files, which are called SS tables. SS tables and index files are read-only files, which is a little bit weird when you think about databases. I'll cover how those work. All right, so here we have awesome time series data coming in. It comes into the write-ahead log, which is just an append-only file. If you've read the stuff that the Kafka team has put out, like append-only files, this is the best possible way to write data. You can write data so fast. You can saturate your disk. You can go crazy with it. So once you write it to the log, you also write it to an in-memory index. Go code. There's Go code here. Okay. So it's not interesting, but I'll get get to it. I'll get to it. So we have an in-memory cache. Here we have a lock, and we have the cache, and we have what's called a flush cache. The key is the series key that we had before. This I think is actually really important, which is mutexes. I swear, every time I look at a brand new Go programmer's code, there are channels being used everywhere where channels should not be used. They get abused, and it's horrible. It's kind of like Ruby programmers and metaprogramming. So yes, for some use cases, particularly for caches, mutexes are your friend. They're the easiest and cleanest way to get Goroutine safe code without having to have like all these gymnastics around messing with channels. So one weird thing we have is that we can have values come in out of order, so we also keep a flag that says whether or not the values have to be sorted. So let me talk about what the values look like and why the sorting thing matters. So we use interfaces here because we can have different types, right? We can have floats, ints, bools, strings. So we just say a value has to conform to this interface. We can get the time, the value, and the size of the thing. Here is the values slice. So we can see we have these methods. We can encode it to get a set of bytes. And then we have the sort methods. The sort methods point out something important for me with Go. And something that many, many people bring up as a problem about Go, right? No generics. No generics, I have to copy code. I have to cut and copy code and do the same thing all the time, and it's horrible. At first it annoyed me, and now I just don't care. I like the simplicity that not having generics in the language provides. It makes the code more readable, and if the sacrifice I have to make to get more readable code is to occasionally copy and paste and have a little bit extra code, I will make that sacrifice because I read a hell of a lot more code than I write, and when I look at my own code 6 months later, I want to be able to understand it. So readability is, for me, one of the most important things, and one of the things that attracts me most to Go as a language and as a philosophy for the designers who put it together. Okay, so this was just something that I thought was kind of interesting. I hadn't used this before. This is out of the standard library. So finding a specific time within the cache, right? We have a collection of values. We know they're sorted. Now, one way to find a specific time in a set of sorted values is to just loop through the array and go until you find it, right? Time on that is going to be O of n, roughly. But the Go library has this nifty little function built in, search, sort.search, and just does a binary search through a sorted array, which is O of login, right? Which is good. Okay, now digging deeper into the storage engine. We do periodic flushes to the on-disk index. Now we can talk about that index. Here's what it looks like. We have a collection of data files. Each data file has a contiguous block of time, right? We know it goes from there to there. The other key thing is that these data files are non-overlapping. They have the exclusive block of time each. So I mentioned before, data files are read-only. They're kind of very much like LSM, like SS tables in LSM trees. And the other thing that makes it very similar to an LSM tree is that periodically a background process will run and it will compact these data files into one larger data file, which is good for us because it keeps the file count low, and we also are able to achieve better compression when we compact more data together. So let's look at this process. So going back here, we can see we have these different ranges, and the compacting is happening in a background process. But at the same time, we're always writing in new data, right? It's time series data. Most often you're appending new data. So the thing that we wanted to enable was we wanted to be able to do these compactions on these files while the appends were coming in. So we didn't want the two to be mutually exclusive. We didn't want to have like one write lock for the entire database. So we basically just created something called a write lock where you can lock a range of time. right? You have lock range, it has a min and a max for the time. You have the unlock. So the thing about lock range is that it should block until we get the exclusive lock on it. There's way too many locks in a Go talk. I know there should be more channels, but whatever. There will be channels, one sec. I don't think the lock code is particularly interesting. It's also, I haven't refactored yet, so it's super gnarly, and I'm embarrassed to show it up here. But one thing that I thought was kind of cool is, I was thinking about, like, how do I write a test for this thing, right? Like, the thing I want to test is that I can get the lock and that it actually returns, or if I try to get a lock that's not supposed to return, that happens, right? That it actually doesn't return. How do I test that something didn't return if it's just supposed to sit there and deadlock for a while? Basically, how can I test that? And this is what I came up with, right? I came up with using channels and a select, right? So we have the right lock, we lock a range from 2 to 10, and this test case is an intersecting range where we're intersecting to the right? So we create a lock channel, we create a timeout of, in this case, just 10 milliseconds, and in a Go function, we lock the range, and we go back to the channel. Actually, there's one thing I didn't have in here that I forgot, which was a wait group to ensure that the Go function actually requests the lock before we continue the test. Pretend that's there. So then we do a select, and we try and get back from the lock channel or back from the timeout. If it times out, we're all good. If we actually got back from the lock channel, we know we were able to request a lock when we shouldn't have been able to request a lock. Okay, that's that piece. Back to the data files. So let's look at the layout of the data files. This is what they look like. Again, it's very similar to an SS table. We have a byte sequence at the beginning that identifies it as this type of file. We have compressed data blocks. Then we have the index block, a min time, a max time, and the count of the number of unique series that are contained within this file. So yeah, it's similar to SS tables. The data block looks like this. We have the ID for the series ID for the data block, and we have the length, which is a uint32 of the compressed block. And the first 8 bytes in the compressed block are the minimum timestamp of the block. The index looks like this. Basically, we have the 8-bit IDs, the uint64s. We have a uint32, which is the position, and we just have that for all those. And the thing about the index block is all the entries are sorted by ID, right? So when we write this file, we keep a list of the sorted IDs, and we say, okay, let's write this index so that they're all sorted. This becomes important later. First, let's look at the data files. We have the file handle, we have the size of it, and we have this byte slice here that we're going to use later. We're going to memory map this thing. Memory mapping lets the OS handle caching for you, which is awesome. And it also allows us to have a huge block of data that's accessible to us as a byte slice that the garbage collector doesn't know about. So we're hiding from the garbage collector, even though the 1.5 garbage collector is glorious, I agree. So this is the code for doing a memory map. It's in the syscall package. I just put it up here because I hadn't used it before, so I thought it was kind of interesting. But once you do this, then you can access the entire file, the contents of the file, kind of like a slice, right? So here, we're getting the min time. And see, the min time, we know it's a well-defined position in the file. We get the position of that. We get the bytes for the actual time, and then we convert it to an N64. And there you can see the d.mmap thing. We're actually accessing it just like a slice, which is pretty awesome. I don't think I have time. I'm going to skip over this. I'll put my slides up and you can see this later. This is basically binary search through the index so that we can know where an ID is in the index. Okay. I want to talk about compression really quick. This is what the compressed blocks look like. Basically, we keep, unlike some other compression schemes for time series data, we actually keep the time and the value compressed bytes separate. So timestamps, we encode them based on the precision you're using and the deltas. So we use different encoding schemes depending on the timestamp. In the best case, we use an encoding scheme called Simple 8B. It's detailed in this paper here. So if you search on that, you'll be able to find it. For float 64, we use delta encoding. It was most recently written about that I know of in a paper that came out of Facebook about a metric system that they wrote internally called Gorilla. So if you just Google Gorilla time series Facebook, there's that. Damien Grisky wrote, I have no idea if I'm saying his name right, he wrote Go code to actually do this, but it uses in32 timestamps. They only use second level precision, which obviously we couldn't do. But we did borrow his float code. Booleans are bits, which is obvious. In64s use double delta, which is nice. For strings, right now we're just using Snappy, which is the same compression that LevelDB uses under the hood. Later we may introduce like dictionary encoding schemes and that kind of stuff. If you have many, many strings that are repeated, then we can get much better compression. All right, wrapping up. How's it perform? How's it do? So the compression depends really on the shape of your data. What precision timestamps you're using, what data type. Even if you're using floats, the compression ratio will vary depending, like if you do random floats, that's the worst possible thing to compress. Whereas if you wrote in a bunch of floats that were all the exact same value, that's the best thing to compress, because then we can compress every single one of those values except for the first one as a single bit. So write throughput, it depends on the batching size, right? Like for us, the best performance is if you take a lot of points and you batch them all together and you send them to the server. It also depends on CPU and memory. Right now, on this storage engine, CPU seems to be the thing we're bound by, not by I/O, amazingly enough. So we ran a test last night. This is on early stuff. It was 100,000 separate unique series, 100,000 points per series, so it's 10 billion total points. It was on a C38XL in AWS, and the writes were coming from 4 different systems in AWS that were writing into it. And each of those systems had a concurrency of 10. So I guess it was 40 total writers coming at it simultaneously. For the total run, the average performance was about 390,000 unique individual data points per second, and the size on disk after the compaction ran, I mean the compaction runs while the write is occurring, so it's incremental, but after the write happens, it will do a full compaction after everything's cold. That size on disk was about 3 bytes per point. And again, that was with random floats. So in real life data in time series generally doesn't look random, so I would expect to get slightly better compression than that. And this 3 bytes per point figure also includes all of the metadata that we have, right? It's the tag data, it's everything. It's not just the raw time series, but it's all the tags and all that stuff so that we can actually do searches on it. So on the system, we saw generally about 400 IOPS on it, which I guess is more than a spinning disk can generally do unless you're in a RAID array, but easy for an SSD. We found about 30 to 50% CPU. We were actually pegging one core, and a lot of time the others were kind of sitting idle, so there's room for us to improve there for the CPU utilization. But we'll have a detailed write-up about it next week, and we'll put out a nightly build so that other people can test against it and break it and make it fall down and all that stuff. So that's all I have. Thank you.
Thank you very much, Paul. Do we have some questions for Paul? Okay, we'll start right here. Do you want to do the mic thing?
It's horrible, right?
It's terrible.
Oh, God. So embarrassed.
Oh.
So, in your data file, why do you have the index at the end?
Because we write all the data first. We don't know the positions for the IDs. So it's easier to just write the index at the very end once we have all that. the first implementation I did wrote the index at the beginning, but then I had to seek back to the beginning of the file, write the position, seek 8 bytes forward, write position, seek 8, it was stupid.
I've personally had to give up a couple personal projects because the standard library just wasn't performant enough, particularly the gzip compressor. Have you found places where pure Go could be made more performant, or specific libraries that you wish were better?
I would love to tell you yes, but sadly our performance problems are the result of my shitty code. So, I mean, we use gzip just because the HTTP is our way to get data into the API. But again, like when we're constrained, we've found our constraints to be not because of standard library performance, but things that we can do to shuffle things around and change things. The GC, we haven't gotten to the point where we're actually testing like really, really large heaps. Right now, the metadata index is kept entirely in memory, so that's what tags, fields, and measurements exist. But with 1 million unique series, it's still fine. It probably won't be as good if we had, say, 50 million or 10 million unique series. So that's really where I'd get concerned, is like what the GC performance looks like when we have, 20 gig heaps.
So I was wondering about the consistency guarantees that you guys were aiming for in this new engine.
I mean, the engine is really for a single server. It's a single thing. So the writes are durable by default. So when you do a write, it'll.
That's Paul's calendar.
Oh, hey! Don't look at that.
Everybody, quick, look.
So when the write goes into the write-ahead log, it serializes it, writes a compressed blob to the file, and does an fsync, and then returns. So once you get a response, you know that it's durable. For the clustering stuff, that's still in alpha. We're still working on it. It's going to be it is eventually consistent. That's the design we've gone with.
Okay, thank you very much, Paul. So appreciate it. So we have a few announcements before we break for lunch.